If I make more mistakes than normal, that's the reason. Okay, so one concept you might talk about in a physics class is a concept called work. Have you heard of this before? So tech, and it's not like, just kind of ish how hard something is, sort of. But the technical definition is that work equals force times distance. Okay, so distance is obviously self-explanatory, right? Like you know what distance is. So force you can think about as the push or pull on the object, is the push, pull on object. And I suspect that in like physics classes, you probably do a lot of stuff in the metric system, right? This textbook does stuff both in the metric system and in the US customary system, so you have to know how these two things are different.
Maybe the second one because they hate us, right?
Actually, in this case, the US system is easier. The metric system is a bit harder because you have to account for the acceleration due to gravity. So in general, the other technical definition of force is mass times acceleration. Okay, so we're going to do the metric units versus,
So it's going to involve derivatives.
it's going to involve integrals.
Okay.
Yep. Okay. So work is force times distance, and force is mass times acceleration, right? Okay, so what is mass usually measured in metric?
Kilograms.
Kilograms. So this is going to have units kilograms. Acceleration, if you think to like an applicate, so this is just like looking at the units of this. So acceleration, if you're thinking about this is going to be meters per second squared. And then distance is going to be meters. So if you're working in the metric system and you think about the units of all the things you're working with, you're going to end up with kilogram meters squared per second squared. Holy moly, okay? So this thing has another name. That's called a Newton.
So it's a Newton
Uh-huh, so work can be thought of as a Newton meter
or joule.
or a joule, yep.
Yeah. Don't see what's so hard about that so far.
Nothing, actually. It's just that it's harder. You have to, so when you're working in this system, you have to account for the whole acceleration due to gravity. So for acceleration, you have to use 9.8 meters per second squared. Like you're going to have to put that in for your A every single time. Does that make sense? So if you see metric, you're going to have to input this for the acceleration to figure out what the force on your object is.
On Earth.
Hmm?
On Earth.
On Earth, yes, on Earth. Okay, we're not going to do any moon questions here. Yeah.
Are all of the work examples going to be vertical, so the acceleration is always going to be due to gravity?
Yeah.
Okay.
You probably do harder stuff in physics. We're going to do pretty basic stuff
So
here.
we're not doing anything with friction?
Okay.
Okay.
No. Okay, now in the US system, so you still have work is force times distance. Now, the thing about the US is that pounds is a unit of force. So this is just going to be pounds times probably feet. So this one has units foot-pounds.
Sounds like a unit of torque.
Yeah, I don't know enough about physics to know what that actually is. Notice that when the question was asked who's taken physics, one person's hand didn't go up, and that hand was mine. All the physics I've learned is from teaching calculus. It's a long, complicated story is why I didn't take physics. Okay, so later. So, yeah. So the point is that with the metric system, if you see metric units, a couple things. The meters is default in there, so you have to make sure that your stuff is in meters. The same as with the second one is you have stuff in feet. So if you're given things in inches, convert them into feet. Does that make sense? Okay. And also don't forget the whole 9.8 meters per second squared. due to gravity. So you have to watch out for those things like on WebAssign because they're gonna give you a problem. You've gotta know, okay, do I need that 9.8 or not? The thing that kind of bugs me about this is this means that pounds and kilograms aren't kind of the same kind of units, which bothers me a little bit because we measure body weight in both of them and we convert between them, but they're not the same thing. And so it makes me cringe inside. And
Well, there's pounds force and pounds like mass.
anyway, it just bugs me because we're going to leave it at that. So really simple scenario. How much work is done in each of the following situations? So you're lifting a 2-kilogram book off the ground to put it on a deck that's 2.5 meters high. And the acceleration due to gravity is 9.8 meters per second squared. So work is, I boo-booed this. We're gonna need force. Work is force times distance, and force is mass times acceleration.
So, this is probably gonna tell us in a second, but is A negative?
Is the acceleration negative? No, I think A is positive.
Depends what direction.
But we're definitely always using positive A.
It's always going the same direction.
Positive direction, acceleration's down. So
Yeah.
negative. But if the positive direction is down, then acceleration's positive.
I think that you always use positive A.
So, well, and basically you're just trying to mass acceleration, you're just trying to find the mass in Newton. Or
In
the-
this case, we definitely always use positive A, and I just need to think back to my calculus 1 for a second. I just can't remember in front of all of you, but I think you also use positive A there too.
Yeah.
negative work, so that should be the
Yeah, so,
You know, you can,
Yeah.
the force of gravity is downward, but the force that you're exerting on the book is counteracting that, so it's upward.
yeah, there you go. Okay. So, what's the mass of the book? 2. So let's put it in units, because I think your physics people make you do that, right? 2 kilograms. Acceleration is
9.8,
meters per second squared, and then the distance you move the book is
2.5.
2.5. So you get calculator question, 49, and the units are joules, yep, or Newton meters.
I wish where integration came into that.
It didn't, but don't wait. Don't worry, you're going to see eventually. How about lifting a 50-pound child 5 feet off the ground?
Wait, isn't that all the math we need to do?
Yeah, so force is
Foot-pounds?
50, yep, so that's pounds. The distance is 5.5 feet, so this is 50 times 5.5 is 275 foot-pounds. What if you were to hold that child 5.5 feet off the ground? There's no work, yeah, no distance. Don't think about work as how hard it is, because obviously I can't hold a 50-pound child in front of me for very long, right? But like I had a physics person explain to me, like, well, if the kid was on a table, then that would make a bit more sense. But just think technical definition, no distance, no work.
And basically, you just need to have a constant force holding the child that
Yeah.
counteracts its gravity.
Yeah, so we're not going to get into stuff all that complicated. We're going to just handle some simple cases like springs and things. So now in the case of many situations, the force is not constant. Does this idea make sense? Like suppose you take a spring and you pull it out. It's easy to pull it in the beginning, requires less force, but requires more force the further you get the spring from its resting position, right? So we're going to deal with situations where the force is actually a function. Okay, so here's the idea. You have, and maybe we can graph this function. So there's a function, y equals f of x, and this is the force function. A to B, and this axis is the distance axis. And this axis is the capital F, or the force axis. So like at a distance of A, the force required is whatever the value of that function is. Right there, the force is bigger compared to here where the force is lower. Okay?
This is gonna just be the generic.
This is the generic example, yep. So some of the force functions you might have might be linear. Most of the ones we're going to see today actually are going to be linear functions in the end. Okay. So we need to find the work for moving a small chunk. So like we take this piece, and we're just going to call that, usually you call it x sub I star, meaning it's some point within that interval. So how much work is it going to be to move that piece?
Area under the curve.
Yeah, it's going to kind of be the area under the curve. So what you can say is, well, I can find the work is force times distance. I find the force using the function, right? So that's f of, it's an approximation, f of plug in that number. And then times the distance that you move, and the distance is this distance along the x-axis, which is delta x. So this part is the force, this part is the distance, and that's for moving just a little piece. So the total work you get by adding up all the pieces. And you go from 1 to n, so piece 1 to piece n. And that should also be an approximate thing, not an actual thing, because it's just an estimate. And then how do you make it exact?
Make the pieces infinite.
Make pieces infinite, which then makes it into an integral from a to b. And so if you have a force function, you just add up all of the forces over your distances. So the kicker for lots is going to be finding those force functions in the first place. And that's going to always revert back to this little definition thing. Okay, it's this far times this force times this far kind of idea. Okay. All right. Suppose you have a particle located a distance of x feet from the origin, and this is the force. Okay, so that graph crosses the x-axis at 0 and -5. It's a parabola. Looks like this-ish. You care about the work done moving this object from 0 to 2, where this is the thing finding your forces. This one's really, really simple. You're given the equation that tells you the force, right? So to find the work, you add up all of those forces. So integrate from 0 to 2, x squared plus 5x dx. So that's what, x cubed over 3 plus 5x squared over 2, right? And 0 to 2, which is what, 8/3 plus 2 squared is 4, 20 seconds. So 8/3 plus 10. 8/3 plus 30/3 is 38/3. And this has units of force, so that's pounds. This guy has units feet. And actually, in that case, you can think, oh, the area under the curve, its units are taking, right? See what I'm saying? That units multiply, so this is foot-pounds. On a couple of the quizzes that I graded, it was just a few, maybe not even this class, when students were asked to find an area under the curve, they said, oh, units squared. But that assumes the x and y have the same units. Does that make sense? So the units on what would be in the area under a curve depend on what the situation is. And the x and y axis could have different units, in which case it's not like units squared, it's x units times y's units. Okay. All right, so one thing that probably will come up in quizzes or tests is something that involves springs, because you see springs a lot in this class and future classes. So this is something called Hooke's law that says that the force required to maintain a spring stretched x units beyond its natural resting length is proportional to x. And what that means is that your force function is given by kx, where k is some positive constant and X is not too large. So what is that thing trying to say?
You didn't destroy the spring.
You can't just take the spring like out past a point because it isn't physically possible, right? So, and we're never really going to get into the whole X is not too large part in this class, but just keep that in mind that that's there. And it should make sense that the farther you are from rest, the more force is required to hold that spring, right? Okay. So here we go. Let's look at an example with that. So we have a force of 12 pounds is required to hold a spring stretched 3 inches beyond its natural length. How much work is done in stretching it from its natural length to 6 inches beyond its natural length? So first of all, you have this f of x equals kx equation, which you have to make specific to this situation. If you have a tougher spring, you're going to have a bigger k. A slinky doesn't require much force, right? Okay. So you know that the force is 12 pounds when you're 3 inches beyond natural length. And so in this force equation, x is how far beyond natural length you are in feet. So 3 inches implies x is equal to how much feet? 3 out of 12 or 0.25 or a quarter feet, right? Okay. And what you know that f of 1/4, when you plug in 1/4, what do you get out? What's the force needed? 12. Does that make sense? Or plugging in 1/4 is the same thing as having k times a quarter, isn't it? So therefore, 12, k equals 48. Great. And so your force equation,
But would that be like pounds, feet, or pounds divided by feet?
well, so far it's the force equation. So in this case, it is just measuring pounds.
But didn't you divide by feet?
Didn't I divide by p?
Or by feet?
I divided by feet. Okay, so we have constant times number times feet equals pound, constant times 1/4 foot equals pounds. I think that a k is just going to have units as well.
Yeah, it's the
So it's not really a problem. Okay, so that's the force equation. So this is how the force is changing. When you stretch your spring 0 feet, it requires 0 pounds. 1 foot requires 48 pounds, right? Okay, so how do you find the work to go 6 inches beyond the natural length?
half a foot.
You integrate from 0 to a half, and you put in whatever your force equation is, which in this case, our force equation is just that 48x. The half is because it's a half a foot. Yep, you have to use feet. So what's that, 24x squared from 0 to a half? Do you guys agree? So that's 24 times a quarter minus 0, which is 6. And then what be this guy's units?
Pounds.
Foot-pounds.
That really is easy.
No, it's not that bad. It's just knowing how to use that kx equation.
No, we're talking about the metric.
Oh, yeah.
versus
The standard, the US customary system definitely in this instance is a little bit easier, I think. Yeah. Okay, this one it's similar, but you're given stuff in a little bit of a different form. So you have 4 joules of work that you need to stretch a spring from its natural resting length of 30 centimeters to a length of 40 centimeters. How much work is needed to stretch the spring from 35 to 40? Okay. All right. So were we told anything about the force in this thing? Not directly. No, we're told what the work is. Does that make sense? So we know that work is equal to 4 if x goes from now, the acceleration due to gravity thing will get built into this question. It'll get built into that whole constant K, but you do have to put those centimeters into meters. So what is 30 centimeters as meters? 0.3 meters to 0.4 meters. And if we found work, what have we done to that force function? We've integrated it. So I know that work is equal to the integral from sum A to sum B of my force function. I know the work is 4. When I integrate from 0.3 to 0.4, and the function I'm integrating is just that k times x function. I just don't know what k is.
Can you take the derivative?
Can you take the antiderivative? 'Cause
No,
you're-
I mean, you've already got the antiderivative, so you can work backwards on that.
Yeah, I think that's what I think you are saying the right thing. So now you can work backwards and you can find the k, that's what you're trying to say, right?
Yeah.
So what's the antiderivative of kx? K over 2x squared, and you're gonna evaluate that from 0.3 to 0.4, right? So that's gonna give us, can I say 8 just by multiplying that 2 over? Is that all right? Okay, so 8 equals, it was a terrible 8, let me fix that. 8 equals k times 0.4 squared minus k times 0.3 squared. Oh, I made a boo-boo. I'm sorry, but at least we didn't plug in any numbers. Erase this, erase that right side, okay? The question was tricky and it was trying to trick me and it did because it succeeded. I'm so sorry. Erase your bounds.
It should be from 0 to the point, right?
Yep, exactly. Do you guys see why? It should be from 0 meters to 0.1 meters.
Because you haven't moved it at all.
Yeah, exactly. Yes.
Can't you pretty much just say it's 4 joules per 0.1 meter and then? assume
No. No, because moving the spring the first 0.1 meter and the second 0.1 meter are not going to be the same amount of work because the force goes up. Does that make sense? Yeah, so unfortunately, no. That would be the case if the force was constant, but the force is not constant, it's increasing. Good question, though. But the nice thing about doing 0 to 0.1 is actually the arithmetic is easier, right? So 8 is k times 0.1 squared. So what's 0.1 squared? 0.01 or 1 over 100. So 8 equals k times 0.01, and so therefore k has to equal what?
800.
Okay.
So really cheap.
Is this your answer?
No. It's just the spring constant.
That's just the constant that you need to actually do the next part of the problem. I'm so sorry. I promise part B is easy, okay? Okay, so how much work to stretch it from 35 to 40 centimeters? So in this work equation, so now you know that your f of x, your force function, is 800x. That's what that told you. But you had to go through all that work to figure out what that silly k was because you didn't know anything about the force, you knew something about the work. So to find the work stretching this from 35 to 40 centimeters, we're going to integrate 800x, and the x is the distance past rest. So 30 centimeters is rest. How much past rest is 35 centimeters? 5 centimeters, or what as meters? 0.05. To 40, which is 0.1, exactly. And the integrals you get here are not super hard. So that's 400x squared, right? From 0.05 to 0.1, and I don't know, guys. I'm going to put these as, what was I going to say? Well, I was going to write them as,
1/10 and 1/20.
yeah, it's actually easier to do that. It's easier to square 1/10 than square 0.1. It's easier to square 1/20th and 0.05. So I have 400 times a 10th squared minus a 20th squared. So 400 times what? 1 over 100 minus 1 over 400, right? What does that end up being? 3. And the units this time are joules. Just want to say one thing, then we'll do part B. So you move this spring, you had this new spring, 30 centimeters. You moved it an additional 10 centimeters. How much work was it to go from 30 to all the way to 40, the total thing?
4.
How much work for this part? How much work for that first part? Does that stem with your, does that jive with what you think it should be? That it should get force increases, so the work increases? So pulling the spring the second half is 3 times as much work as pulling it the first half.
Is that normally gonna be the case?
How big the discrepancy is depends on that constant in your force function. Yep, so if that constant is bigger, I think the discrepancy will be larger. But no, I'm not sure. Is it always 3 times as much? I don't know. I mean, maybe there is a pattern, but I don't know. I would suspect not, but there could be. Okay, so part B, this is actually a lot easier. How far beyond its natural length would a force of 300 newtons keep the spring stretched? So is this asking about work?
No.
No, it's asking about force. What's the force equation? 800x, right? What we just found. And we want to know what's the distance past rest that this will keep the spring stretched. So how do we find that? Solve for x. Yeah, put the 300n in for f of x, because that is, and you end up with x is equal to 3/8. And that would be meters past rest.
Should you find that in like a decimal equivalent?
Not if you're putting the answer into WebAssign. Well, and I guess, 3/8 will be a decimal that terminates. In that case, you could put the decimal into WebAssign. But if you have like 8/3,
Because you're dealing with meters and they don't really like non-base 10 things.
no, it's a, anyway. The point is how to solve the question, not like the semantics.
It'll work with decimals if you hold 3 down for a little bit. It'll work with decimals if you hold the repeating decimal down for a little bit.
Will it?
Yeah.
If you get to a certain accuracy, it will take it.
Yep.
But that seems like a lot more work than putting in like 1/3.
Yeah.
Right? I mean, like, I just think that's like, okay, I'm going to press and hold this button until it takes my answer,
It's
or,
like 6 or 7 extra 3s.
okay.
Points.
Most of it would be 3. That's like
I find it
9
great that he's
threes.
experimented with this. That's awesome.
Slash key is just so much easier though.
Huh?
The slash key is much easier.
It is, yeah. All right, so you probably will see a spring question on a test. I'm just going to warn you, okay? So you have to know the whole f of x equals kx equation. Now, another kind of question you might see in a test has to do with like lifting heavy chains up buildings. This is a really good physical example because like sometimes people do lift heavy chains and things up the top of buildings, right? This happens all the time. So we have a heavy chain that's 100 feet long and it weighs 3 pounds per foot. And it hangs over the edge of a building 250 feet high. So I always draw a picture. So I have my building, and over the edge hangs this chain. It's fully stretched out. And I'm going to call this x equals 0, like up at top. How far down does it go?
X equals -100.
We're going to count positive, but yeah, x equals 100.
Well, I just figured it's going down.
Yeah, no, I understand that, but in this case, it is helpful to orient your axis. I think you can make that work, but that's not how I'm going to do it. Okay, so how much work is done in pulling the chain to the top of the building? So the tricky thing here is that different parts of the chain move different distances. Do you see what I'm saying? Like this part at the bottom, that moves 100 feet, right? This part in the middle moves 50. This part right there moves 25, plus all the stuff in between.
And you're
So the-
assuming that once you pull the chain to the top, you're no longer pulling that weight.
Yes.
Yeah.
Yep, exactly. So I think we definitely ignore like little bits of this to make it kind of come out nice mathematically. But and then in physics you deal with the more complicated, ugly parts. We don't do that in this class. So the idea is break the chain into chunks. So look at a chunk of chain, like a really small chunk,
Like a foot?
like a foot, like a half a foot, like a tenth of a foot, you know, some small chunk. We'll call it delta X chunk of chain, okay? Because the delta X means we can make it as small as we want. Okay. All right, so work for moving that chunk of chain is force times distance. Okay. So we're going to find the work for moving one chunk, and then we're going to add up all the chunks, take a limit, make it an integral. That's all of the stuff in this chapter involves that. Break into pieces, add the pieces, take a limit, make an integral, get a formula. Okay, so first of all, the distance is the easy thing with this one. So from there to there, the distance you move, because I oriented my axis the specific way, is just given by an x value. Does that make sense? Like if we were right here, that would move 25 feet. If we're down here, that'd move 75 feet. So it's just given by some x sub I. And that's going to have units of feet on it, right? Okay. Now to find the force, we've got to figure out how much does a chunk of chain weigh in pounds. So the chunk of chain is delta x feet long, right? Times 3 feet per, I did that backward, 3 pounds per foot, right?
So,
And so then just multiplying this and canceling units, the work for moving a slice is 3x sub I delta x. And what are the units now?
pounds?
Pounds. Is that what it should be?
No, there's foot still in there.
Oh, no, but that's okay. It is. There's foot pounds. It's a work, right? So work's supposed to have units foot pounds, right?
Yeah.
The size of chain you're moving is delta x. The acceleration isn't necessary here because we've got the American units. You use the 9.8 when you're in the other system. Then when you were finding the force, you would need that 9.8 to get the force. So that's for one chunk. How do you get the total work approximately?
Infinite chunks.
Yeah, you add up, well, officially you add up the chunks, right? So total work is equal to sum of chunks. Then you limit number of chunks and the work becomes an integral.
From 0 to 100?
From 0 to 100, yep. Your chains move between those distances, and the function inside the integrand is 3x dx. Mm-hmm.
Wouldn't it be something like a 300 minus 3x? Because it weighs 300 pounds initially, and then like per foot, it weighs 3 pounds less.
I think that is definitely accounted for in the fact that you do an integral here. Because you think about the weight of one small piece separate from the rest of it. You say I move this piece this far, this piece this far, this piece that far, times how much does that piece? What is the force on that individual piece only? So no, you don't have to do anything like that. Definitely not. Okay, so what's the antiderivative of 3x?
3 halves x squared.
Mm-hmm. From 0 to 100, and that ends up being 1,500. No, I think it's 15,000.
Yeah, you're right.
Now I know why those wenches have those ridiculous readings.
Yeah, they also probably, I think they also add in something for like an error. They don't make it the minimum. They do like this, like times
Yeah.
some factor. So that's the whole chain. Now, what if I think part B says only half the chain, right? Okay. So you pull up half the chain. So you have to think about this one in two pieces. Okay, so you have this first piece. That's the first 50 feet. And you have this second piece that is the next 50 feet. Picture not drawn to scale, okay? We're still orienting the x-axis down, so there's x equals 0. Down here's x equals 100. Now, in that first chunk of chain, does every piece move the same distance?
Still moving.
So in this first chunk of chain, this piece will move a little bit. That piece at the bottom moves 50, right? Piece in the middle moves 25. They all move different distances, right? So that one you handle like the previous one. So you have the total work is equal to the top half work plus the bottom half work.
Oh, because you're still moving the other chain. by
Yeah, exactly. Okay. I think this might actually answer your question too, Mitchell, because you're gonna kind of you'll see with this that the weight of the chain that you're pulling up on the bottom definitely is like accounted for as this is happening.
Well, I was just thinking it's like if we're thinking f of x is the force function, then wouldn't we think that 300, it starts out at 300 pounds, then decreases by 3x each time? Because I got the same answer.
You
that
did? Okay.
I got the same answer, and I predict I'm gonna get the same answer because it's by a squared relationship. So
Show me at class, after class, okay? Because it might. If you got the same answer, it probably is doing the same thing, okay? But I can't like do it right now. Yeah, but I'm happy to look at it after class. Okay, so but going with the method we used for part A, is it clear that moving the top half of the chain, we get the same force function, we just move it from 0 to 50? Is that part all right? Okay, the second part you can handle with an integral, or you can just think about how much does this chain weigh and how far does it move. So how much does that last 50 feet of chain weigh?
150.
You have 50 feet times 3 pounds per foot. Does that make sense? 150 pounds of chain left. And then how far does it all move? It all moves 50 feet. Does that make sense? This piece right here is not the top. This piece right there is at the bottom, but it's all moved 50 feet. Okay. So this is 3/2 x squared from 0 to 50. Oh, so what's that? 3750? I'm just gonna have to believe you because I can't arithmetic under pressure. And all in all, you should get 11,250 foot-pounds.
Okay, so if you've already gone that far, it's not so hard to pull up the rest of the chain.
And that's because the part, when you're doing this part, you're pulling the rest of the bottom part of the chain also a significant distance, right?
Yeah.
So there's work in doing that. That's why the remaining part is less work.
It's a lot less work.
Significantly, yeah. So pulling the chain halfway up is not half of the work, right? That's the kind of the point of this problem. It's almost more than half of the work. Another way to do this, instead of just thinking about what it is, could be that you move it from 50 to 100, like that's the x values range. And it's 3 pounds per foot times 50 feet, as in it's just going to be a constant function. Because the force for that part is just the same, it's always constant. So that if you integrate from 50 to 100 of 150, you get the exact same thing. You get 150 times 50, which is what we had. So your book or some solutions might explain it that way, but I think it also isn't very hard to think about, oh, I just have this random chunk of thing hanging on the end. You know, same as like a kid, just a really tall, skinny chain kid that you're pulling up. Okay. So how about this? So often you don't just pull up chains, you pull up chains with stuff on the end of them, right? So you have a cable that weighs 2 pounds per foot, and you're lifting up coal from a mine shaft. Anybody mining engineering, this matters for you, right? So find the work done. And it's quite similar to the last question. Did anybody see a relationship between the whole pounds per foot and the force equation? That last one was 3 pounds per foot, right? What was the force equation? 3x, that's probably gonna happen again, right? So our force equation, using the same logic, is gonna be 2x. And that's just for the cable.
Would be just like 2x plus 800.
Pretty much, yeah. So the total work will equal the work from the cable plus the work for the coal. And you can definitely do this two ways. So just handling the cable alone, suppose we had no coal on the end, you'd integrate from where to where? 0 to 500 plus the coal. So force times distance, what's the force on the coal?
500 times 800.
800 times 500, yep. Because it's just like lifting a kid up X feet, right? But the thing that's changing, because you're going to not be lifting all of it all the way up, is the chain. Does that make sense? The chain is the thing that's varying, because once you've pulled some up, there's less force acting on the chain, and the distances are also different. But this one is just a chunk of thing that moves X distance. So let me finish. X squared 0 to 500 plus 40 with 4 zeros. Right, so 400,000. Yeah. So what's 500 squared?
250,000.
Yep.
Usually 650,000.
Mm-hmm. Here's a question, because it might actually answer what you're going to try to ask me. Could you use the force equation f of x is 2x plus 800 and integrate that?
Yes.
You get the same thing. Does that make sense? You say, oh, you have this chain plus this force that's always on the end and it's constant, right? If you integrate that from 0 to 500,
You integrate it, you just got.
you're going to end up with 800x, which ends up being 800 times 500, right? So it's the exact same thing.
Are we assuming that either the thing they used to attach the cable to the coal had the same like ratio of weight to length, or it was built into the weight of the coal?
Say that one more time.
Well, they had to hold on to the coal with something.
Yeah. I think that the something that's holding the coal probably is accounted in with that, like as in like the box or whatever, or the, hook, that kind of stuff.
Okay.
Okay. Something like that might also show up on a test or a quiz, but they'll be pretty easy numbers. Like, it's not that hard to square 500, is it? Not if you know rules for zeros. This is a kind of take-home question, because it ends up just being a little bit tedious. So you have an aquarium that's 2 meters long, 1.5 meters wide, and 1 meter deep, and it's full of water. Okay, so here goes. Art class, draw the aquarium. So 2 meters long.
To make it 3D drawing.
Yeah, you do a box and a box, and it's 1 meter deep.
Yours looks so much better.
Yeah, practice. And what you think about here is you want to take, and it's completely full of water, you want to pump all of the water out of the aquarium.
Which direction are you going?
You're going up and out. And the thing that you don't account for with this is you don't account for any kind of like over distance. You just kind of assume I take a layer and then it's at the top and then it just dissipates, which I don't know if it's a realistic assumption at all, but that's how we handle these problems. So you have a little layer of water, lift at the top. Little layer of water, lift at the top. We do nothing with the whole over and out of the tank business. So, and I don't know enough about physics to know how that's different, but it probably is. So you orient it a bit like the problem with the chain. You say, well, I'm going to let x sub I be the distance I lift a slice. So the work for a slice is the force times the distance. Oh, okay, force.
It's just the density times.
Yeah.
Slice, right? Density slice gravity.
Force is equal to mass times acceleration, right? So mass is going to be in, or meters. No, force is MA. So kilograms and acceleration is going to be in. Okay. So do we need the 9.8 in this guy?
Yes.
Yes. Say that louder.
For the last problem, you don't need the gravity because it wasn't in meters.
Because it wasn't in meters. When you're in pounds, no need for the whole gravity thing. You also don't need it with the whole kx equation because the 9.8 can be sucked into the k. Okay. So the force is 9.8 meters per second. Now, how do you get the mass of a slice of water?
We multiply a slice of water by its own density.
So you have volume of slice of water. What's that going to be measured in?
Liters.
I think this one's going to be meters cubed.
Same thing.
Times its density, which is measured in what?
Kilograms per meter cubed.
And will that give you the required necessary unit for this M? Okay. All right. So we're going to find volume of a little slice. The slices are actually all the same volume. Does that make sense? Because they're rectangles. So what's the base of the rectangle, what's the length, and what's the height of just a small rectangular slice?
3xi.
Well, it's 2 meters times 1.5 meters. And I took a little bitty slice, so its thickness is delta x meters. Okay? And then times the 1,000 kilograms per meter cubed.
We can make those numbers get really weird.
Yeah, so the volume of a slice is 3,000 delta x that's not the volume anymore, that's the, because this is the volume. Once I added in the density, I actually get the mass, sorry.
3,000 delta x kilograms.
Mass is 3,000 delta x kilograms, exactly. So you put in your 3,000, and that part alone is your force. And then how far do the slices move if we orient the x-axis down? They range between 1 and 2 meters, but a general thing is x meters down, because you don't know where your x is specifically, just like we did with the cable. So that's an x sub I. And that's the thing that you add up and then integrate.
So we already have a dx in there somewhere.
Oh, and I forgot my delta x, right? Because that came from the whole 3,000 delta x. So total work is an integral. The 9.8 times 3,000 ends up being 29,400. Becomes x dx. And then you have to think, what are the distances that I lift my slices?
0 to 1.
0 to 1. Nope. I think it's 0 to 2.
It's only 1 meter high.
Oh, it's only 1 meter high. Yep, you're right. I was just testing.
Unless you're like trying to levitate it above. the-
Nope. Yep. Some of your homework questions have water where like it doesn't start until 1 meter down. Like you have a tank that's 6 meters deep, and you want to take the water out. Its water's 1 meter below the level, so you go from 1 to 6. Like it's 0 if it's completely full and you're at the top. But if there's a gap, then you have to start from where the gap begins. And the integration is not very hard, so I'm just going to tell you what you get for the answer. This ends up being 14,700 joules. with a little bit different thing there, and the tricky thing is that finding the mass of a slice of liquid of some sorts involves doing its volume times its density. That's the tricky thing. And maybe some of the questions on the homework might involve things like gasoline, whose density is a little bit different, right? Stuff like that might also happen. So just but if you're gonna have to use it for a question, I'm gonna at least try to give it to you like in like the take-home quiz and stuff. This one also wasn't super hard because my slices, no matter where I sliced, were the same volume. Does that make sense?
And is that gonna change?
There you go. Just one, okay, just last one. So the tank is the shape of an inverted point down circular cone with height 10 feet and base radius 5. I don't know why they call it the base because they mean the top, but whatever. The water extends from a depth of 1 foot to 10 feet. Find the work required to empty the tank by pumping all the water to the top. And the weight of water is 62.4 pounds per foot.
Wait, is it a pointed cone or is it an?
It's one of these like, it's an ice cream cone. It's just a really big ice cream cone filled with water.
And somehow able to support its own weight?
Well, I mean, I don't know. I'm from Minnesota, and there are these things that hold corn all over the place, right? I mean, anybody else been in Minnesota at like corn time?
They also use similar things to lift concrete.
Yeah.
Because there's shapes similar to that.
Exactly. So I think this definitely happens. They're just supports that hold it upright, and those don't matter in terms of what we're doing here. Okay. Now, I'm going to orient it like this and put the point of the cone at the origin. There are other ways to do this right, but this works just fine. I think this is the easiest way.
Yeah, it creates symmetry.
Yeah, create some symmetry. And, okay. So the water starts 1 foot down. What's the Y value that corresponds to? 9. Great. Okay. I'm going to take a random little slice and take that little slice to the top.
You're just assuming it's gonna spill out the top.
Well, we did that in the last problem too, okay? So we're just going to assume it just kind of like, once it gets to the top, it just kind of like dissipates, or moving to the edge isn't that big of a deal. So I didn't say it was super, super realistic. Okay, so I'm going to use, I think in Calc 1, you probably solved things like this using similar triangles. As in, so this distance is 5, this total distance is 10. And I need an equation that tells me the volume of a slice. And because my little slice is delta y's, I need to have y's in this equation. So you're finding the work, which is force times distance. But to find the force, you have to find the density or the volume of a slice.
So it would be 10 minus y.
So force, ooh, good, yes. Let's go there in just a second. So the force is equal to the volume times the density. Okay, density is 62.4, and that's pounds per cubic foot. Okay. So the volume of that little thing is going to be pi r squared, right? It's a circle. Does that make sense? But the question is what is that r? Because the r is not always the same, right? If it were like a Coke can, then, or a cylinder, right? Then it would be not a cylinder, what's that called? It's a cylinder. Yeah. It is a cylinder. Okay, yeah. Huh. So what is the r? And you did questions a little bit like this when you talk about related rates in Calc 1. You have this height that is 10. This distance is 5. This distance is y. This distance is x. Does that ring a little bit of a bell? Not at all? Okay. Well, we're gonna use similar triangles, like from geometry, to relate x and y together. Does that part make sense? Mm-hmm. So then what you have is that, well, x over y is equal to 5 over 10, or a half. Therefore, x is equal to 2y. So my radius, that radius is the distance from there out. So then therefore, this is what my radius is. And you can see if that checks out, like if you're at the bottom, your radius is 0, right, when y is 0. If you're at the top, the radius is 5.
That does not work at all.
Wait, if you're at the top, your y is equal to,
I actually think it should be 2.
did I boo-boo? It would be y over 2, yeah, exactly. I shouldn't go so fast. Okay, so x equals y over 2. Not that. Check your cross
Probably
multiplying.
should have started with the top to check that in the first place.
Yeah, the bottom just didn't make sense. Okay. So then what's the volume of a random slice? It's going to be pi r squared. So pi y over 2 squared, and then times delta y gets the thickness. Yeah.
I think it would still be 2y because x over y, x is twice the length of y if you look at the original.
If you cross multiply this, you have 2x equals y, so x is equal to half y.
X in the original problem is 10 and y is 5.
X in the original problem is,
No, if
Yeah,
you look
X
up
is
there,
fine.
the x-axis is the sideways one.
Your little diagram there is backwards.
oh. I just want to go crawl in a hole now. Y, x. But she definitely has y over 2 here, though.
That's because your X is,
That's because I made a mistake in the picture, but righted it when I made the equation. Right? As in I fixed it right here.
yeah.
Oh, God. Okay. All right, so when you multiply all this junk together, you square that y over 2, you end up with 15.6 pi y squared delta y. That's in pounds. That's your force. Okay, the distance is not nearly as hard. Because you're going out the top, the distance a slice moves is how far is it from there to your slice. Okay? So is it just y sub I?
It's 10 minus y.
It's 10 minus y sub I. If you were going out the bottom of the tank, then it would be, nope, not even that hard. Distance from there to there would be just y sub I.
So if you're going out the bottom of the tank, you wouldn't even have to carry, you just cut the bottom off and be gone.
Yeah, but there's, anyhow. So the total work is given by an integral of these two things multiplied together. So 15.6 pi y squared, 10 minus y dy. And what do your y's range from? What's the y down there? What's the y up there? 0 to 9, actually, because there's no water in that top of the tank. Okay, and after all that, we have 15.6 pi, integral 0 to 9, 10y squared minus y cubed, right? I think from there you guys can all hopefully do the arithmetic with a calculator. You end up with 12,320.1 pi foot-pounds. It'd be easier for us to grade if when you do this work on your take-home quiz, you leave stuff in terms of pi, or put both answers there, like put one with pi, one without pi. You know what I mean by multiplying by 3.14, 159, et cetera. Okay.
You look at like 10 decimals.